Okay, let's try that again. Hopefully this is a little bit faster. So this is the HypoTree, and what it allows you to do is take a data set. So we're in a certain environment, so-called problem context, and we're using a certain data set here, and basically we're analyzing that data set. So this allows us to interactively work with not only the data set, but also analyze it with different hypotheses and kind of string those hypotheses into a sort of a tree-like format. So here's a tree. It's rooted. It's always rooted in a constant value. So this constant value, we can see here is this value here. So we have basically it's always going to return this result, and it's going to be it's always going to be the same result. And so you can see here it's the same result for all the values. Now obviously we want to reduce the error. So the error between the sale price here, which you can see here is between about 35K and about 7.5 million. Those are the different sale prices in our data set. So the average here, the average of the entire data set is about 181K. We've picked from a bunch of candidates, 64 candidates. We've picked a winner, and that winner happens to have about 170 odd. 170K is its mean value, but that's fine. We're going to repair that over time. So like I said, we want to add hypotheses to this tree to reduce this overall error here. And so I'm going to show you how to do that. So let's suppose that we decide that let's say the greater living area is related to the sale price. We all kind of intuitively understand that. And so I should point out that we can do this automatically, and this is not. There's a different tool to find the best sort of path automatically. This is a tool to interactively explore what things may go into the actual sale price of the house. So if we see this field here, so this tells us a little bit of information on that field. Suppose, let's say that we want to just get a general scatter plot of not the sale price. So that would be interesting. So we can get that there. You see that's an interesting scatter plot. But we always want to take the y1. So sale price is the value we're trying to predict, but we automatically add fields such as the h underscore and ensemble output. That's what it's short for. And that's the ensemble is all the different, it's the sum of all the hypotheses all the way down to the root. So you're going to see this tree grow, and so that's what that value is going to be. H0 is going to be the current hypothesis, and Y1 is going to be the current hypothesis minus the sale price minus the current hypothesis. So it's going to be kind of the remainder, if you will, or the residual of those values. And so it's going to be at this point, if we look at it here, we'll see that it's basically the average is H, which is at this point in time about 179K minus the sale price, and that is equal to a bunch of different values, so sort of translated to around 0. So so again, if we look at and we say, okay, well, let's take greater living area, and we say, okay, we think that that's going to have some impact on the sale price. So we can say, so the remainder, y1, and let's look at the scatter plot of that. So we can see that, yes, in fact, it does. It's centered around 1 because we subtracted the average price in the first hypothesis, and we see a kind of very kind of, standard relation as we kind of expect. We note here that the density is obviously decreasing as we grow out. So we have a lot of data points on these sort of this area here, but as it goes out, we get a lot fewer data points. So if we take this and we say, okay, well, let's create a hypothesis in regards to the remainder. And this hypothesis is basically going to be a line or a curve, and it's how complex that curve is. This polydegree, so it's a polynomial of in this case degree 2. So that's going to be a constant, a linear term, and also a squared term. And we can go up, in value in that. But let's leave it for now. And this is the number of ones to compete. So it creates a bunch of them to try to compete with each other to see which one is the best. And we'll leave that for 60 for now. So let's create one of those. Sometimes it takes a while. So if we click on that, wait a while, and a new tab will come up. So we see with this new tab, we see here is this line is the green line. This is the estimated value. So that's the new hypothesis, right? So again, this is versus the existing value. So it's always centered at 0. So we see that some of them are below and some are above, depending on the different values. So we have the red is the training data. So the trained data are these red values. So the hypotheses only see sort of half the data. So they see, in this case, it's again a random set of half the data. That's what we call it, training data. And then we have the other half as the test data. So we always training it's two different sets of data. One is the training data, which is a hypothesis can see, and then we test that against the test set of data to make sure that there's no bias built into our model. And so the green is the estimate, so we can see that, yeah, that's kind of what we expect. That's what the line kind of, it's not exactly a straight line. We can kind of see there's a bit of a curvature to it, but it is somewhat a linear relationship. And then the yellow is the error, so it's going to be the the test minus the estimate. So that's going to give us, so we can see here that that's exactly what we want is the error to be slowly reducing. So that this yellow, as we go through, if we look on the far left, we should see that these values slowly kind of creeping towards 0. So that's ideally what we'd like, right? So let's say we're happy with this. And we say, that sounds interesting. So we can add that to the tree node, right? So what this is going to do is going to add this hypothesis to the current node. And so when we do that, expand here, click on this, and now we can see that the average error has actually gone down quite a bit, right? So it's gone down by about 20K there, which is pretty good. So that's great. Now we can kind of look at the remainder. We can see the remainder. We can see the remainder here. The average value has reduced, right? It's the average sort of. If we look at the dispersion, which is kind of what this number is a measure of, that dispersion has kind of gone down a little bit. And as you add terms, that'll go down farther and farther. We've all heard so that was a sort of a linear relationship. So we can imagine there's a sort of a continuous variable there. So obviously there's 10 square feet, 100 square feet, 1,000 square feet, so on. It's a continuous. So the values can take on any sort of continuous value in that range. And but there are also sort of categorical variables, and so let's look at sort of a typical one, which is neighborhood. We all heard of location, and so we expect that the sale price is definitely going to depend on location. So let's look at that. So if we look at if we just want to get a kind of brief look at how the two relate. So we're going to take this again. We take the highest y value. That's the residual, right? And let's look at a visualization of that. So yes, so again we see that yes, in fact it does look like it. We see each one of these groupings. It seems to be higher or lower, and there's a different sort of dispersion and probability distribution for each sort of area. So we see the areas down here at the bottom. So that looks fine. So let's go ahead and create a hypothesis for that too. It's a slightly different type of hypothesis. Again, it's categorical values, so it's a little bit different. And we might say, well, let's take 16 different types of them. So again, we out of have multiple different. So this in this case it was 64. Now it's 16. So we take all these candidates and we pick one, and that winner was the least mean square. That's LMS. That's for continuous variables, and this one is this is a different hypothesis, and this is for categorical variables. So let's have a look at that. And so we see we found a winner here, and what this is showing here is saying it's looking at all the different neighborhoods, and it's saying, okay, well, how does this? So if we look at BRDale looks to be a nicer neighborhood, right? So we expect the center of this distribution to be above 0. So if we go back over to here, do BRDale, see no, that's not true. The center measure is slightly below the average value. So sorry, I was looking here. So the BRDL, sorry, is right here. So this is actually a little bit below 0, and so I thought it was this one. So if we look at Somerset, there we go. There, it's a little bit higher. So we can see that the average values. This is if I told you that here's the square footage of a place, and then I said, okay, and further here's the area of the neighborhood of the place. This is how much it would change from the existing values. In this case, just no matter what the square footage was, if the square footage was of the lot was accounted for, we see if it was placed in Somerset, you'd get an additional 42K, right? And if it was in BRDale, you get actually a negative 37K on average in the value. But again, it's a probability distribution. So this is only the expected value. The dispersion measure and some of the other variables are also here as well. So the key things here are, first of all, the center measure. This is the expected value, right? The second thing is the dispersion measure, and you think of that as the standard deviation. N is also very familiar to most people. So how many samples? What's the strength of that sample? And so that's another key metric. And then there's the max, and so on. That's you can kind of ignore for now. And so we can see here that generally the higher the n, the more sure, the more strength the result has, and the lower the n, you can see how it actually prunes out lower values of n automatically, because just the uncertainty around that will actually add uncertainty to the model. So you kind of want to get away from that. So let's suppose, again, we say that's something we want to include in our model. So we hit add this one again. So it adds it to the current one. So now we have 3 different items, and we can see that this has reduced the error quite a bit, but not as much as the first. So we see that the sort of a diminishing return as we add these sorts of things. So the first, when we added the living area, that gave us a huge improvement. We added the neighborhood, that gave us substantial but smaller improvement, and we expect that's going to continue. That as you add features, as you compensate kind of for the price, compensate for the information you have, the x values, the neighborhood, and greater living area, and so on, then we expect that the error, the average error, which between the actual sale price and the predicted one, will reduce. So now let's suppose you want to actually test some of these out. So you flip over to the test panel, and the test panel will takes a random kind of value. So in this case, it's the 673rd property in our data set, and you can just play around with that. There's a random one, you get 966, and so on. So you get a certain random values. So these are all the random values, and now we can say, well, what if the lot area, let's say the lot frontage, is in the existing class is 75. So that's the value it's going to be. But let's see if we can predict the results. So let's look at the results. So we see that the results are, we predict 164K roundabouts for this particular house. The actual sale price was 158 roundabouts, so it's not too bad. And this this value is not just this value, but it's also made up of several other results. And so what are the results? So first one, obviously, is this first value here, which is the average value. So we take the average value, we take that into account. And then we say, okay, well, given that, we take the next thing into account, which was the greater living area. And we said that that was about 1,400 square feet, and that was seemingly, this was lower than average. So so that actually subtracts from the price of the house. But and this is a key point. Given that, given these two pieces of information, after that, we try to take into account the neighborhood, and we see that in fact this neighborhood is not a good one on average, after taking into account the lot area, and that subtracts a further 10K from the house. And so if we add up all those things, we get the value of about 164K, which is a pretty good result. But now let's suppose that you say, well, what if we were in some way somehow we're able to increase the greater living area, right? So in this case, let's find the greater living area. What was the last place to look? Square foot. So I say great. So let's suppose we say it's going to be 3,000 square feet instead. So we set that. So now the square living. So we'll see that now. So now the greater living area is now 3,000 square feet, which should give you a higher price. So instead of a negative 3,000, we should see a higher price. Let's say do the results again. So we see, wow, that gave us a lot. So we actually, greater living area was 3,000. That gave us a huge amount on the price. And so now, wow, so it was a huge house in that area, and so it really increased the price. So we can see here that we can kind of play around with different results and build a very complex tree. And so we're not limited to this branch of the tree. We can go from any sort of area. So if we said no, instead of the neighborhood, we want to actually go from the greater living area to let's say let's just say the garage area. So we say, well, let's go from instead of, like I said, the greater living area to the neighborhood, let's say what if we take into account the garage area as well? So look at that, quickly in the scatter plot, and we see that, yeah, it seems like it does have an effect. So let's have a look at that. So we say, well, let's configure this, 16 hypos, and we'll create that, go off. Hypo there, and boom, we see that yes, it's somewhat of a straight relationship. Again, it's centered around 0, and again we reduce the error a little bit more as we go. And so we say, fine, let's add that. Now it adds it to the current one. So we see now that we have two branches We have one where I explored neighborhood, and one where we said no, let's take into account garage area first. And what if we further said, okay, let's take into account the actual neighborhood. Go on neighborhood. We go to the last one again. We'll do 16 of them. 16 competitors. Create that again. And we see that, yes. So in general, as we go through here, you'll see that these values kind of slowly decrease, but not to 0 or something like of that nature. It'll decrease, but not to 0. So let's add that to the tree as well. And now we can see that there's a sizing bug in my program here. So anyway, so we can see here that now the error has gone down. But interestingly, it didn't go down as much as not taking into account garage area first. So that's one of the interesting aspects of machine learning. The order that you account for things actually does matter. So there is, even if you account for the same things, if you do it in a different order, it actually can give you a better or worse hypothesis, and that's part of kind of a fundamental aspect of machine learning. But anyway, that's kind of most of what I want to cover. There's one last panel here, which is a hypo panel. So this tells you exactly about this specific hypothesis, or sorry, the entire hypothesis to the root. So we see here that it's the ensemble of gradient boost variety. We're looking for the sale price. It's an ensemble based on 4 hypos. Let's look at each hypo. So the first one is the constant. Second one is the greater living area. The next one is garage area. And then the third one is this based on neighborhood. And if we go to a different node on the tree and click on this, then you can see it's a different set of hypotheses and different values and so on. So that's most, I think, of what I want to cover. Thank you for listening.